Now at the very beginning of chemical bonding, we have learned that there are essentially two kinds of chemical bonds. One of them is when a metal combines with a non-metal, and the other one is when a non-metal combines with another non-metal. Okay, when a metal combines with a non-metal, it will form what we call an ionic bond. And then when a non-metal combines with another non-metal, it will form a covalent bond. Alright, in the last lesson we have seen how an ionic bond forms, what is an ionic bond, and how can we represent ionic compounds. In this lesson we're going to learn the same for covalent compounds. So we're going to look at the same three things: how is a covalent bond formed, what it is, and how do we represent covalent compounds. Now we have briefly mentioned that covalent bonds are formed when a non-metal combines with another non-metal. Okay, and we have also learned that non-metals, they need to gain electrons. Both non-metal atoms needs to gain electrons in order to become stable. Alright, since both atoms need to gain, no one wants to give away, they must learn to share. Alright, so a covalent bond is formed when the two non-metals share electrons, alright, between two non-metals to achieve again their noble gas electronic configuration. So this is how a covalent bond is formed, by the sharing of electrons. Now I'll illustrate with an example. The simplest of example would be hydrogen. Hydrogen has one electron only, so this is the electronic configuration of hydrogen. Is it stable? Answer is no, because it doesn't have a fully filled valence shell. So hydrogen as an element, it cannot exist as an atom. But how? It can actually combine with another atom of hydrogen. Okay, hydrogen atom needs to share one, the other hydrogen atom needs to share one. Okay, so how can they share so that both are equally happy? Is that they will share one each. Alright, so by sharing their one electrons, you can see and recall that after sharing, the electrons belong to both atoms. So by sharing, both hydrogen atoms will now have two electrons, and when they have two electrons, they have a fully filled valence shell and they are stable. Okay, so that will bring us to what is a covalent bond. Remember, by the word bond, it means there's some form of attraction. Okay, the attraction is very obvious in an ionic compound where we have a plus and a minus. Alright, in fact, all kinds of bonding involves some form of plus and minus. However, the plus and minus is not so obvious in a covalent bond. Okay, so where does the plus and minus hide in a covalent bond is here. Alright, recall that your electrons are negatively charged. So this part is negatively charged. Okay, hydrogen atoms, they contain protons in the nucleus. Okay, so there's actually some form of attraction between the protons in the nucleus and the shared pair of electrons. Okay, this attraction is again between plus and minus, so we call it electrostatic attraction. Okay, between protons in nucleus and shared pair of electrons. Okay, so once again, a covalent bond is the attraction between plus and minus, electrostatic attraction between the protons in the nucleus and the shared pair of electrons. Okay, what is a covalent bond is not exactly in the syllabus, alright, but it will be good to know. So as mentioned, a covalent bond is formed when two or more non-metal atoms, they share their electrons. And after sharing the electrons, there will be some form of attraction between the protons in the nucleus and the electrons that are being shared. So this attraction is known as covalent bonding. Now we'll go on to the third question of how can we represent covalent compounds. And same as for ionic compounds, there are three ways we can represent them: by their name, formula, and dot and cross diagram. Okay. For covalent compounds, there is a less emphasis on naming it, but rather when given the name, you are supposed to know what is the formula of the compound. And very often, the formula of the compound can be inferred from the name. Okay, so for example, when we look at the first one, carbon dioxide. Carbon dioxide, from the name, we can infer that it must contain the element carbon, it must contain the element oxygen. Okay, but how do we know how many carbon combined with how many oxygen? In the name of the covalent compounds, very often you will see this words or this phrases called prefixes. Okay, the prefixes will actually tell us the number of that element, the number of atoms of that element. Okay, so by the word di over here, di actually means two. Alright, so dioxide means you have two oxygen. Alright, now we look at the next example, nitrogen monoxide. Nitrogen monoxide, from the name, we can infer that it must contain a nitrogen and an oxygen. Okay, how many of each? If there's no prefix, the default is there's only one of it. Okay, and sometimes when you see the word mono actually stands for one. Okay, so what are the prefixes that you need to know? Mono stands for one, di stands for two, tri is three, tetra is four. All right, that is the most that you would need to know. Okay, so if we look at the next one, carbon tetrachloride, it means that it contains carbon and chlorine. How many carbon? If there's no prefix, by default is 1, and tetrachloride means there are 4 chlorine, so the formula is CCl4. Now unfortunately, for many covalent compounds, there are common names for which you cannot infer the formula, but you just have to memorize. The three most common ones would be water, ammonia, and methane. Okay, water, H2O, ammonia, NH3, and methane is CH4. So for these three covalent compounds, there's no way you can infer the formula from the name. You just have to memorize the formula. Okay. Okay, so now we'll look at how we can represent covalent compounds in the form of diagrams or dot and cross diagrams. Now the key to drawing a dot and cross diagram for covalent molecules is that for each molecule we need to list out all the atoms that are present, and for each atom to find out how many electrons does it need to achieve a noble gas configuration, and this number of electrons will be the number of electrons that it needs to share. Alright, so for example, we look at the first one, which is hydrogen molecule. Hydrogen molecule is made out of 2 hydrogen atoms. This is the electronic configuration of the 2 hydrogen atoms. Each hydrogen atom will need to share 1 electron in order to have a noble gas configuration. Alright, so how do we share it? Each hydrogen atom will share 1 electron with each other. Okay, so by sharing 1 electron, you can see that the hydrogen on the left will now have 2 electrons, the hydrogen on the right will now have 2 electrons, because the electrons that are shared will now belong to both atoms. Okay, So there's a way to represent the shared pair of electrons, which is by the use of a single line. Alright, so we can represent a hydrogen molecule by H dash H. This line actually represents a covalent bond. It actually represents the shared pair of electrons. Okay, now let's take a look at the second molecule, which is oxygen. Oxygen is made out of 2 oxygen atoms, and each atom has an electronic configuration of 2.6. So that means that both oxygen atoms need to share 2 electrons in order to have a noble gas electronic configuration. So how do we share it? Is that each oxygen atom is going to share 2 electrons with the other oxygen atom. Now the important thing for oxygen is to notice that oxygen has 6 valence electrons. That means that after sharing 2, it will have 4 more electrons that are not used for bonding. So a common mistake that students make is that they will forget to put in the remaining electrons. Okay, so now if you check the oxygen on the left and on the right, they will now have 8 electrons each. Okay, so once again we can represent each shared pair of electrons. We can actually represent it by a line. So we can simplify, or we can represent the structure of oxygen by 2 lines. Okay, by 2 lines it means that there are 2 covalent bonds. Alright, or we call it a double covalent bond. Alright, which is represented by 2 shared pairs of electrons. Now we look at the third one, which is nitrogen. Nitrogen is made out of 2 nitrogen atoms. Each nitrogen atom has this electronic configuration. So both nitrogen atoms will need to share 3 more electrons in order to become stable. So how do we share? Once again, they will share 3 with each other. Okay, so once again we need to take note that nitrogen has 5 valence electrons. So after sharing 3, there will be 2 valence electrons remaining. Please remember to put in the remaining electrons. Now if we look at the electrons that are shared, there are 3 pairs of electrons that are being shared. So what it means is that there is actually a triple covalent bond, a triple bond between nitrogen atoms. Okay, and the triple bond is represented by 3 pairs of shared electrons. Now we'll continue to look at the drawing of dot and cross diagram for more molecules. The examples here are slightly more difficult because now we are looking at atoms of different elements. Alright, so there's one additional approach or one additional step involved. Okay, so same thing if we look at the first example, which is water. Water is made up of 2 hydrogen atoms and 1 oxygen atom. Alright, now we need to write out the electronic configuration for all 3 atoms, and then from there we can find out that your hydrogen needs to share 1 more electron to become stable, whereas oxygen needs to share 2 electrons to become stable. Okay, so now the problem is how do we share such that all the atoms get the number of electrons that they require. Okay, the trick is this: you always put the atom that needs to share more in the middle. Alright, so oxygen needs to share more electrons, so we put it in the middle. Oxygen needs to share 2 electrons, so essentially it can share 1 with 1 hydrogen and share the other electron with the other hydrogen. So you will get something like this. Okay, so bear in mind again that oxygen has 6 valence electrons, so after sharing 2, it will have 2 electrons that are remaining. Okay, so over here, since we have two different elements, we need to show a legend to tell people that cross represents the electron from oxygen, whereas dot represents the electron from hydrogen. Okay, and another thing that I have yet to mention up to now is this, is that in most dot and cross diagram questions, you will see this term that they will ask you to show valence electrons only. Okay, most of the questions you will see this term, show valence electrons only. Okay, that means that you do not have to show the inner shell electrons. However, should a question not state that you show your valence electrons only, then in that case it will be safer for you to draw out any inner shell as well. So for example, in water there's actually the oxygen actually has an inner shell. Okay, so if a question doesn't state to show only valence electrons, you will need to show your inner shell electrons as well. However, if it says that you only need to show valence shell, then there's no need to show your inner electrons. Okay, so in the drawing of dot and cross diagram, many students will also encounter this, that you will have your hydrogens in a horizontal fashion. Okay, in the context of O levels, we are likely to not mark you wrong. However, it will be good to know now that the structure of water is actually like that, where the hydrogens are arranged or positioned in like an inverted V shape. Alright, we call this a band shape. Alright, so this is the actual structure of water. Why is it like that? We will learn it when you go on to higher levels, and you learn how atoms are arranged to maximize the stability. Alright, so bear in mind that water, the arrangement of hydrogen and oxygen is in the form of a V shape. Now we look at the next molecule, which is that of ammonia. Ammonia is made up of 1 nitrogen and 3 hydrogen atoms. Okay, so we look at the electronic configuration, and from the electronic configuration we can figure out that nitrogen needs 3 more electrons, so it needs to share 3 electrons, and there are 3 hydrogen atoms that needs to share 1 electron. Okay, so how do we share such that all atoms get the required number of electrons? Again, the trick is to put the atom that needs the most electrons in the middle. Alright, so nitrogen needs to share 3. There are 3 hydrogen atoms that needs to share 1 each. Okay, so nitrogen will share 1 with each hydrogen. So this is how the dot and cross diagram will look like. Again, nitrogen has 5 valence electrons, so take note that nitrogen has 5 valence electrons. After sharing 3, it should have 2 remaining. Okay, so this is the dot and cross diagram for ammonia that shows only the valence electrons. Okay, so if you can recall that we can actually represent a shared pair of electrons by a line, the structure of ammonia will look something like this. Okay, with a pair of electrons. Right, and the last thing of course that we need is the legend to tell us that cross represents the electron from nitrogen, and then dot represents the electron from hydrogen. Now the next example would be carbon tetrachloride. Okay, for carbon tetrachloride there is 1 carbon atom and 4 chlorine atoms. So you write down the electronic configuration. Carbon is 2.4, chlorine is 2.8.7, which is the same for the other two as well. Okay, so therefore carbon needs to share 4. And then if we look at the 4 chlorine atoms, each one of them will actually need to share 1 more. Alright, remember for non-metals, for group 4 to group 7, they need to gain 8 minus the group number of electrons. So chlorine needs to share 1. Okay, so how do we share such that all atoms get the required number of electrons? We put carbon, which needs to share 4 in the middle. Okay, so carbon needs to share 4. There are 4 chlorine atoms that needs to share 1 each. So carbon can share 1 with each chlorine atom. Okay, and the important thing about this is, of course, chlorine has 7 valence electrons. After sharing only 1, it would have 6 remaining on each chlorine atom. Okay, so we need to fill in our legend. This time cross stands for the electron from chlorine and dot stands for the electron from carbon. Okay, and with each shared pair of electrons representing a covalent bond, we can represent the structure of carbon tetrachloride as follows. Okay, bear in mind that each line represents a covalent bond, which is a shared pair of electrons. Now we look at the next example, which is carbon dioxide. Carbon dioxide is made up of 1 carbon atom and 2 oxygen atoms. Okay, carbon atom has the electronic configuration 2.4, and then oxygen atoms have the configurations 2.6. So the next step is to find out how many atoms how many electrons do each atom need in order to have a noble gas electronic configuration. And for that, carbon atom needs 4, so it needs to share 4 electrons. Oxygen atoms, both of them need to share 2. Okay, so once again, how do we share in order for each atom to have the required number of electrons? The trick is to put the atom that needs to share the most in the middle. So carbon needs to share 4, and there are 2 oxygen atoms that need to share 2 each. So the ideal would be carbon sharing 2 with 1 oxygen and sharing the other 2 with another oxygen. Okay, so the dot and cross diagram for CO2 will look something like this. Alright, bear in mind, now if we look at carbon atom has 4 valence electrons. It has already shared 4, so it has no electrons remaining after sharing. However, for oxygen has 6 valence electrons, so after sharing 2, it would have 4 electrons remaining. Okay, so we add in the legend. Okay, and lastly, if we take a look at the dot and cross diagram for carbon dioxide, you will notice that between each carbon and oxygen atom, there are 2 shared pair of electrons. So what it means over here is that between each carbon and oxygen atom, there is a double covalent bond. Okay, and for carbon dioxide, it actually has a very strict arrangement of the atoms. We call this shape a linear shape. Alright, so there's, if we were to measure the angle between the 2 bonds, is actually 180 degrees. Now we will look at the very last example, which is also the hardest. This molecule N2H4 is known as hydrazine. Okay, so it's made up of 2 nitrogen atoms and 4 hydrogen atoms. Okay. Now, even though this is an unfamiliar molecule, the approach is still the same. So you must first write down the electronic configuration for all the atoms, followed by finding out how many electrons it requires for it to achieve noble gas configuration. So let me just very quickly write down the electronic configuration for all the atoms. And then from there, we can find out that nitrogen atoms need to share 3 electrons. Okay, and all 4 hydrogen atoms need to share 1 electron. Alright, so as to how do we arrange the atoms such that, or how do we share the electrons such that all the atoms gain the required number of electrons, for this example it's going to be slightly trickier. Alright, but if you can remember the rule of putting the atom that needs to share the most in the middle, alright, that will lead you to the correct diagram. Alright, so there are 2 nitrogen atoms. Both nitrogen atoms need to share 3. So we put them in the middle. Okay, since now we have 2 atoms in the middle, the 2 atoms must somehow be connected to each other. Alright, so this nitrogen can actually share 1 with the other nitrogen atom. Okay, now after sharing 1, each nitrogen will still want to share 2 more. Alright, so and there are 4 hydrogen atoms that wants to share 1. So essentially, we can have 2 hydrogen atoms sharing with each nitrogen atom. So the dot and cross diagram will look something like this. Okay, now bear in mind again that nitrogen has 5 valence electrons. It has only shared 3, so there are 2 electrons that are not involved in bonding. So let me just write in the legend. And lastly, once again, remember that each shared pair of electron represents a covalent bond, and the covalent bond can be represented by a line. So the structure of hydrazine will look like this. Okay, a very common O-level MCQ question is that they will give you a structure of a molecule that looks like this, and then they will ask you questions like how many electrons are involved in bonding. In order to solve the question, all you need to do is to count the number of lines and then multiply it by 2, because each bond, each line represents 2 electrons. Alright, so for example, in this case of hydrazine, the number of lines would be 5, or rather the number of bonds, there are 5 covalent bonds, so there are 10 electrons involved in bonding. Now here are some common mistakes that students make when drawing dot and cross for covalent compounds. Right, the first of which is forgetting to write legend. Alright, and then the next most common one, of course, is to forget to put in the non-bonding electrons. Alright, I'm going to show you an example now, which is carbon tetrachloride. So most of the time when this molecule comes out as a dot and cross diagram, students tend to draw something like this. They will remember that carbon needs to share 1 with each chlorine atom. So this is the most commonly drawn dot and cross diagram, which is wrong. Okay, reason being chlorine has 7 valence electrons, so after sharing 1, it should have 6 remaining. Okay, so please bear in mind this common mistake that students make, and do not make them in your own assignment or test.